Most programming in ROS is based around the idea of nodes, which are self-contained processes. ROS provides a framework for communicating among nodes in the form of topics and services. All messages transmitted in one of these formats must adhere to an interface. Such interfaces are explicitly defined in ROS, and they allow both the sender and receiver to know exactly what to expect. While ROS comes with a number of built-in interfaces, you will often find that you need to define your own custom interfaces. In the previous episodes, we built our own nodes that acted as publishers and subscribers to topics, as well as clients and servers that responded to service requests. We did this both in Python and C++. In this episode, we will build on those examples by defining custom interfaces. You will see how to define a message interface for topics, as well as a service interface. We'll modify the publisher, subscriber, client, and server examples to use these new interfaces. Let's jump in. If you head to Concepts Basic About Interfaces in the ROS2 documentation for your particular distribution, you can learn about interfaces here, and we will be covering most of that in this video. There are three different types of interfaces. We have messages. These are for topics. We have services. As you can probably guess, these are for services. And then we have actions. Actions are not something we will cover in this series. They're a more advanced topic that we won't get into. Messages, or message interfaces, are made up of one or more fields. These fields are strongly typed, so you have to give a particular type, and then you have to give that field a name. So for example, here is int32, the name of that field, and then it's also followed by a string, and then the name of that string. So these two together would create an interface. ROS2 has a number of built-in field types that you can use. So when you're creating your interface, you should use one or more of these field types and describe your fields. We have everything from Boolean for yes or no, 1 or 0, true or false, single bytes, characters, strings, floats, integers, unsigned integers of various bit widths. If you scroll down, you can learn about constants. You can set constants here, and you can also use services. Services are a little different because they have a request and they have a response. The request and response are divided by this dash, 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 which we will see when we create our own service interface. You can have nothing in these to demonstrate that the request and response go out with no fields in them. This is useful for triggering something, for example. But in each of the request and response section, you can also have one or more fields that you need to fill out here. Now let's go about creating our own interfaces. The recommended practice for custom interfaces is to create a package that's separate from your code packages. If we go into source, you can see that we've worked on our C++ and our Python packages. These have the code that run our various nodes. Generally speaking, you will want to keep an interface package that is separate from your other packages so that either or all of your packages can depend on it when you're trying to send messages back and forth. Let's go to View Terminal, and we will create a package for our interfaces. Let's go into that src directory. You can see our code packages there. We will call ROS2 package create as we've done before. We will give it the build type of CMake. That's because the generators in ROS2 create both C++ and Python code from the interfaces that we will define. As a result, it's usually easier to do this from a CMake package. So we will use the CMake type here. Then we will give it a name, in this case, my interfaces. Let me correct this spelling error. Let's use build type instead of built type. Once that's done, refresh your files and you should see my interfaces created here. And that is a bare bones CMake package. cd ... to get out of that source directory. This does start as a package with the assumption you're going to be creating nodes in here. And we're not going to actually write source code. So we can get rid of include. Let's delete that. Delete permanently, and we can get rid of source. Delete, move to trash, delete permanently. Yes, we end up with CMakeLists and package.xml that has some boilerplate in there for us. Let's create a new folder in here. We're going to call it MSG. This is the messages folder for topics. And we're going to create SRV. This holds our interfaces for services. Inside of MSG, let's create a new file. And we're going to create one called accelerometer.msg. If we do ROS2 interface list, you can see a list of all the built-in interfaces that come with ROS2. There's a bunch of stuff in here I recommend using, so you don't have to create your own interfaces. For example, points. You might have transforms, twists, vectors, lots of things dealing with space. You also have Excel for acceleration or accelerometers. In fact, you should probably use that instead of the one we're about to create, but we're going to create our own accelerometer message so you can see how to create your own interfaces. Let's scroll down back to the beginning of that. And we're just going to create a very basic 3-axis accelerometer reading. We're going to store each of these axes in 64-bit floats. So we'll say float 64, X, float 64Y, float 64Z. And the idea is something can publish accelerometer readings using this interface. Let's Control S to save that. We will go to package.xml. Make sure you have ament CMake as your build tool dependency here so that ROS knows which tool to use to build this package. We also need to include the generator here. And this is the ROS systems interface definition language. That's IDL, so ROS IDL. And then the default generators. This defines the way to describe messages, services, and actions in ROS2. This is required for converting your interface definition files into code that Python and C++ know how to use. Then we need to depend on the default runtime tool. This ensures that the correct artifacts are linked for runtime usage, things like .so shared libraries for C and C++ or .py modules that get included when you run your Python code. Finally, we have ROS IDL interface packages. We will tag this with member of group. This tells Colcon that this is a pure interfaces package. It should not expect to find any executable code like nodes in our ROS package here. Control S, let's save that. And we will open up CMakeLists.txt. Under find dependencies, let's get rid of these comments. And we will tell it to find the package ROS IDL default generators. And we will say this is a required package. Once again, these generators are used to generate interface code for C++ and Python. Before ament package, where we say everything before this constitutes our package, we need to add a few lines here. The first thing we will do is call this ROS IDL generate interfaces function. This is where, instead of listing out the executables here, we're going to list out our interface files to explicitly tell the generators what interfaces it needs to generate into C++ and Python code. We will list those each on a line. The first one is in the MSG directory, and that's accelerometer.msg. That's the file we just created. We need to export the ROS IDL runtime as a dependency so that anything that imports this interface package automatically gets that runtime. It doesn't need to explicitly import it, and it just saves us another step, and we don't have to modify our code that much. Let's save this, Control S. Down in our interface, let's build the package. So we will call colcon build, as we've done before, -- packages select, and then give it the name of the package, my interfaces. Let that run for just a moment. With any luck, you should not see any errors. Click that pop-up to make it go away. If you go to your workspace, go to install, go to my interfaces. If you go into include, you can see the generated header files here. And if you go into lib, Python 3.12, site packages, my interfaces, you should see the generated Python packages. And if you get out of that Python library, you can see the .so files. These are the shared objects used by C++ when everything gets compiled and linked. Let's get out of this install folder. If you go to VS Code, you can create a settings.json. And in there, you can say python.analysis.extrapaths in quotation marks, colon, and then a list here. And we can tell IntelliSense in VS Code where to look for these packages because they're not installed in the normal Python 3.12 location. So first we tell it to look in the Jazzy distribution, the installation folder, where to find the site packages there. And then we can tell it to look inside of this workspace install, and where we just saw that lib Python 3.12 site packages folder, that will be the Python packages for our custom interfaces. And as JSON, these should be encapsulated in curly braces. So save that. In many cases, you might need to refresh VS Code, so I will shut it down, bring it back up. It should read that settings.json file. and we should be ready to go. So I'm going to close out these files as soon as that extension finishes setting up. And now we can write our demo. We're going to start with Python. So let's close that source. Let's close my interfaces, install. Let's go to source. Let's go to my Py package. This is where we've been writing our own nodes. We're going to copy minimal publisher. So we will copy that. And then I'm going to paste it in that same folder. I'm going to rename it to ACC_publisher. And we're just going to modify that publisher node we created earlier in the series. I'm going to get rid of that terminal so you can see what's going on with the code. Instead of this example interfaces string, we're going to import our own interfaces because we've refreshed IntelliSense and told it where to look for our new packages. This should appear for us where we can just autocomplete my interfaces. It will have MSG. We're going to import, and you can see it already has accelerometer here for us. So that is our new interface. Instead of minimal publisher, we're going to say ACC publisher for accelerometer publisher. We're going to say it periodically sends out dummy accelerometer data. Instead of minimal publisher, call it ACC publisher. When we create that publisher object, it's no longer a string type. It's an accelerometer type. We will change the topic from my topic to my ACC. The rest of this is the same, so it periodically calls this message. Instead of a string message, this is an accelerometer message, and it no longer has this data field. You can see it's already filled out because of IntelliSense. So the first thing we have is X. So we're just going to put some dummy data in here, and we'll pretend this is like meters per second squared or something. So X is 0.5, Y is 0.1, Z is -9.8. Then we will publish the message to the topic. In this case, this stays the same, and we can get rid of counter here since we don't need it. Let's get rid of counter here. We don't want it. And this is no longer minimal publisher. This is ACC publisher. The entry point stays the same since all it does is fire up our node, known as ACC publisher, and just sit there and run it. So let's save that. Let's go to setup.py, and we're going to tell it to include ACC publisher as an executable, and I need to give it the package name. Let's save that. Let's view terminal, and we're going to say callcon build -- packages -- select and my Py package. With any luck, that should build. Let's go to our run desktop. We're going to bring up a terminal here, and we'll go to our workspace directory. Don't forget to source that setup.bash file in the install folder. We'll call ROS to run my Py package, and we'll give it ACC publisher. It looks like I missed something here. Accelerometer object has no attribute named data. And if I go to ACC publisher, there is no data field in message. But what we can do is just call message, and the message object should, by default, have a toString function that is called when we try to print it as a string. So this should, in theory, print out what that message looks like. Let's save that. We will build it again. Looks like it succeeded that time. I'll push up to go to the last command, ROS to run ACC publisher. Sure enough, there it goes, printing the message. And you can see the object here, my interface's message accelerometer, and the data that's being published. Let's bring up another terminal. Let's go to our workspace. We need to source that setup.dash because remember, that also includes our custom interfaces now. So if you list those interfaces, you should be able to go up to messages here. And we called that my interface's message accelerometer. So you can see our custom interface appearing in that interface list. Let's go back down. Let's see what topics are available. And let's go ahead and echo my ACC. Sure enough, it should be getting that XYZ that's being published to that topic. I'm going to Control-C and stop both of these. Let's go back to our code. Now that we've seen it in Python, let's see how to use it in C++. So I'm going to close down the files I've been working with. Let's minimize those folders, go to my CPP package. Let's go to source. And before we start messing with anything in here, let's update IntelliSense. So in .vs Code, go to CCPP properties.json. We can configure IntelliSense in here and tell it where to find those interface files that have been generated. So under include path, this is where IntelliSense looks for things like interface files. Let's add a new item here. This $workspace folder in curly braces is a variable known in VS Code. This is the current workspace. In this case, it's going to refer to config workspace. And if you remember where we saw those header files, that's going to be in the install folder, my interfaces include, and then we're going to do **, which says look for everything under there. So it will look for all of those .h.hpp files that constitute the header files for this custom interface. Control S to save that. And in many cases, you will find that you need to restart VS Code or do a refresh. So I'm just going to close it down and start it back up. And now IntelliSense should pick up those new settings. We will go into my CPP package under source. Instead of the publisher, let's do the subscriber this time so you can see how the Python and C++ nodes communicate with each other using our custom interface. Let's copy the subscriber. We will paste it in here. I'm going to rename it to ACC_subscriber. Instead of the example interfaces string.hpp, I'm going to do my interfaces MSG, and you can see IntelliSense automatically picking up those files since we updated that properties.json. I've got a red squiggle here, which is interesting even though we updated that include path. This should be fine. I'm going to do ACC subscriber as the name of this class. Instead of the constructor name of minimal subscriber, we'll change this to ACC subscriber, and we'll change the node name also to ACC_subscriber. We're going to create a subscription object. Notice here we're using this template to say example interfaces message string. That is now going to be my interfaces message accelerometer. The function binding will be the same since that callback is still called listener callback. And there still should be one placeholder for the message there. Under that callback, instead of message.data, we're going to print the XYZ to the console. So I'm going to get rid of that. I'm going to put this down on another line to save us some space here. And then we're going to say accelerometer : and then we will print out the X, Y, and Z values. We will use %.2f to print out floating point values rounded to 2 decimal points so that we don't hog up the whole console. And then we will fill those out with message.x, message.y, and message.z. This member variable has the type of example interfaces message string. So we need to change that to my interfaces message accelerometer. And the same thing up here, this type of message being passed in should also be changed to my interfaces message accelerometer. Let's save that with Control S, and we should go to package.xml. In addition to example interfaces, we depend on my interfaces. And as you probably just guessed, it is something I forgot to do in the Python package. So let's copy this because this is a dependency on a ROS package. These package.xmls should be pretty similar, and I'm going to paste that into the Python packages version here. As you just saw, Python works without declaring this. This is generally considered a best practice in ROS2 to list your ROS package dependencies in this package.xml. Things may compile and run without it, but it's usually considered very good to list them here in this package.xml. So I will paste that there. I will save that. This is the C++ one. It's right here, ready to go. Save. Let's close that file. And then in CMakeLists.txt, under find dependencies, we have to list our dependency here. And we will find package my interfaces, and we'll say it's required package. We also need to list the target here for compiling our executable. Just like we did for the minimal subscriber, we will add the executable target, ACC subscriber, tell it where to find that source code, which is in source, acc_subscriber.cpp, and then we will tell it where to find the dependencies. In this case, we will call the ament target dependencies function that's unique to ROS. We will give it the target, ACC subscriber, and then we will give it the two main dependencies here, which is RCL-CPP for all those good ROS functions, and my interfaces instead of something like example interfaces. Then we will need to list the target down here to install the binary. Save that with Control S. We'll go to View and Terminal, and we'll say callcon build packages select my CPP package. With any luck, that should build and install. Looks like we got a couple errors here. I probably kept the name minimal subscriber in somewhere. Let's go to our CPP. Sure enough, in subscription, this needs to be changed to ACC subscriber. And down here where we run the node, also ACC subscriber. Let's save that and we will try to build again. Looks like it built this time. So let's go on over to our run desktop here. I'm just going to push up and start running the Python version of the publisher. In this other terminal, we need to source the setup.bash again, since we've added that new executable, so that the ROS command line tool is aware that that executable exists. Then we will say ROS2 run my CPP package and ACC publisher, not publisher. We actually want the subscriber. That's not printing anything. And I think I realized what my error is. So I'm going to Control-C to stop that. I'll leave that publisher running. Let's go to the subscriber. And it's probably where we instantiated this subscription tool. Here we go. We subscribe to my topic. Nothing is being printed to my topic. So we need to change this to my ACC. If we go to the MyPy package and we go into ACC publisher, sure enough, I had changed this to my ACC. So make sure to save the CPP file. Let's build again. That built. Let's just run that CPP file, that subscriber. And sure enough, there it goes. It is subscribed to that topic and is printing out the X, Y, and Z that were filled out in that message interface. Let's Control-C to stop that. Let's call ROS2 interface show my interface's message accelerometer. That prints out the information of that interface file we created earlier. So you can see X, Y, and Z. And this is a good way to get information, even if you wrote the interface file yourself. As we saw earlier, ROS2 has a number of built-in interfaces. If you look in the geometry messages, there's message accelerometer or Excel. You can see here there's actually already an interface that this is very similar to the one we already created. In this case, it gives you both linear and angular acceleration data. This is probably the one you would want to use for accelerometer data, but as I mentioned, this was a demonstration of how to create a custom interface. Let's stop the publisher with Control-C. And now that you've seen that, note that you can also use messages in other messages. Let's see how to create an array of messages, but we will build a service interface this time. Let's call ROS2 interface list. If we go up to those topic message interfaces, we go to that geometry messages. This is a good starting point for lots of built-in message types. You can see there is a message and a point. So we will say ROS2 interface show geometry messages message point. That will give us some information about this point. This contains a point in Euclidean space, so we have floating point values of X, Y, and Z. And let's say we want to create something like a service that's based on this, and we can have an array of these points. This might be, say, path points that a robot needs to drive to, or say a point cloud from a couple of rotating LiDAR sensors. Let's go back to VS Code. Let's shut down the files we've been working on. Let's collapse these. And we'll go into source in our workspace. We'll go into my interfaces. Inside of this SRV folder, we're going to create a new file, and we're going to call it trigger points. So the request will be a number of points it wants the server to send back, and then a response that is an array of those. So the request here is num points. We will say that is an unsigned integer up to 16 bits. As you've probably guessed, the hashtag or pound sign is comments in these interface files. 3 dashes is to divide the request from the response. So we will first respond with some sort of success. That's a Boolean, so true or false. And here's where we can use that other interface as a type here. Instead of sticking to those fundamental types, we are going to use that geometry messages point. We're going to give it open close brackets to say that this is an array, and we will give the field a name. In this case, we'll call it points. Let's save that. We'll go to CMakeLists.txt, where we list out the files we want to build into code for those interfaces. We will add SRV and trigger points.srv. Let's save that. We also need to update package.xml. And after this member of group, we can list out our ROS package dependencies here. And recall that the first part of that name, that geometry messages, is an actual ROS package. So we're going to list that here as a ROS package that our interface depends on. Control S to save. And now we need to go back to CMakeLists. Even though we've added our interface file here, we need to find the package. Again, we need to list that dependency, not just for the package's sake, but also for the actual build system. And we will say that geometry messages is a required package that CMake should find. And then under here, we need to list our dependencies. So we will use capital dependencies, and we will list that geometry messages. So that's how ROS knows to use other interface packages as dependencies when building out our custom interfaces here. Control S to save, and we will call callcon build -- packages select my interfaces. With any luck, that should build. So let's close down these files. Let's minimize my interfaces, and let's start with a Python package. We're going to copy minimal server. We're going to paste it. So we've cloned that in my py package. Let's rename that to trigger points server. Let's close down this terminal, and we're going to add a few things here. I'm going to include the built-in random library from Python. And then instead of this example interfaces, we're going to change this. We need to include the geometry messages message point because we need to create a point object in order to encapsulate that in our custom message. And then we need to import trigger points here from our messages that we just created. So our server is just going to respond to one of those requests with an array of random points. Remember, this is a test. Those could actually be filled out from, say, a sensor. And we're going to call this trigger points server. Let's make sure to rename the node to trigger points server. In our service object, instead of add to ints, we're going to give it the type trigger points. We'll give the service name trigger points as well, and then we will modify the callback here. So let's get rid of what's going on in this callback, and we will just say we're going to respond with an array of random floats that actually meet that point interface. We will log the request number of points found in that request here. We will set the success part of the response based on the number of points requested. So if the requester requests 0 or maybe a negative number, if it's able to send that because we said unsigned integer. So basically, if it's 0, success will be false. If it's greater than 0, we'll say success is true and not num points here. Let's say success is equal to false. So we will create an empty array here for the points in our response, and we're just going to loop through the number of points that were requested. So we'll just say 4, we don't actually need the index here, in range and those number of points. If these end up being 0, then this is not called. I'll scroll down so you can see what I'm doing. We're going to define a point that comes from those geometry messages, and we're going to fill out the XYZ in those points, and we're going to set each of those to random.uniform. So that gives us a uniform random variable between, in this case, -1 and +1. We will do that for Y as well as Z. And then we will append that point to that array and then return with that total response. Down at the bottom, so I don't forget this again, we're going to rename this to trigger points server. So that way it runs the correct node. Let's save that. Let's go to setup.py. Underneath our accelerometer publisher here, we are going to add our trigger points server as an executable. So Control S to save. If we go to package.xml, even though we have my interfaces here, it's not including those geometry messages. So just like we added in the package.xml, where we depend on geometry messages, in fact, we could copy this. So I'm going to copy that line. I'm going to go to the package.xml for my py package, and I'm going to paste that right here. That dependency does not get transferred over when we say depend on my interfaces here, so we have to include it again here. Let's save that. Let's go to view. We're going to go to terminal, and we're going to say callcon build packages select my py package and let that build. Hopefully that completes without error. Let's go to the other desktop. We need to source install setup.bash again because we added a new executable so that the ROS2 tool knows about that executable. And let's ROS2 run my py package trigger point server. Looks like I have an error in here. Aha. It looks like I'm trying to import trigger points from the messages. And remember, that was an SRV, not an MSG. So let's go to trigger point server. You see I have MSG here. This should be SRV because this is a service interface, not a message interface. So we will save that. Let's build again. Looks like it completed. Push up in the run terminal. Let's try to run it again. And I see nothing, which probably means the server is working. In the other terminal, let's type ROS2 service list. You can see this custom trigger points being broadcast here. And we need to source install setup.bash again so that the ROS2 tools know about the custom interface that we created. And then we're going to say service call, the name of the service, trigger points in this case, and the interface. So my interface is service trigger points, and then we will fill out that call. In this case, in curly braces, in quotation marks, we're going to say num points is 3. And service is not a standalone tool. So let's not forget the ROS2 part of that call. So with any luck, when we run that, you should see the request being received by the server over here, received request, num points is equal to 3. And you should see the response coming back from our dummy call here, and it should fill out an array of 3 points. So here's your point type from geometry messages. We have X, Y, and Z. These are randomly filled out. We have another point here, and then the final point is given right there. So it looks like our server is indeed working. Let's go back to our code. Let's close down this terminal. Now let's demonstrate this again using C++, but we're going to create the client this time. So let's minimize my interfaces and my py package. Let's go to my CPP package. Let's go to source. We'll go to minimal client. We're going to copy that. We're going to paste it here, and we're going to rename that to trigger points client. Let's close down some of these other files that are taking up the tabs up here. And I'm going to Control Z out of whatever I just accidentally pasted there. So we include RCL CPP here. We can get rid of this example interfaces because we're not going to be using that. And we're going to include geometry messages, message point.hpp. And if you see IntelliSense not showing up there, I'm going to save this. I'm going to refresh VS Code. Hopefully IntelliSense picks it up again. So let's try it here. Let's see if it knows about SRV. There it is, trigger points.hpp. It took just a moment. Once again, I'm getting red squigglies here, even though IntelliSense did find that. If you happen to know a particular config setting that I forgot, let me know in the comments. Instead of minimal client, we're going to call it trigger points client. I'm going to copy that and paste it for our constructor function. Instead of minimal client, we're going to call it trigger points client. We will create a client object here. Notice the template. This template is now incorrect. We're going to say SRV trigger points. And here is the service. We're going to say trigger points is the service name, and that should match up with the one in our server. We will wait for the server for a little while. That doesn't need to change. We will seed the random number generator, and we will periodically call the timer callback message. This should all be the same with the exception of this namespace here. This should be changed to trigger points client so that it matches the class we're in. We're going to make this a little more generic and just say send request to server. In this callback, we're going to fill out the request, and we're going to say, let's request a random number of points. So where we make the shared pointer here, instead of example interfaces, we're going to say the type is my interfaces service trigger points, and all the generated code should have this request type in there, which helps us make a shared pointer for this particular request. Let's get rid of that. So the request, we're going to say num points in that request, and we're going to say it's a random value between 0 and 10. We can do this standard library random function modulo 11. That gives us between 0 and 10 inclusive. Then we're going to send the request to the server and set the callback. So instead of minimal client here, this is the trigger points client. We'll set the response callback. The rest of this stays the same. Then in this callback, we want to log the results when we receive it from the server. So we want to get that future, but this will not be an example interfaces add to inst type here. This will be a trigger points type, shared future. So future.get, we get that value. Auto figures out the type for this resp or response variable. Then we want to call RCL CPP info, but we're going to construct this a little differently. So in there, we will say get logger from this object. We will first print the success. C++ does not have a nice toString function like Python does for Boolean types. So we need to use this operator to say, hey, if success is true, print true, and if it's false, print false. Then we will do a for loop. If you haven't seen this format before in modern C++, instead of looping through an index, we're going to loop through elements in an array. So this single colon in the conditional essentially turns this for loop into a for in loop. So for a point in the resp points, and we get a pointer to that individual element. We're going to then loop through each of those points and print their values to the console. So RCLCPP info, and then we will get the logger as we've been doing. I'm going to scroll down so you can see what I'm doing. And we will print the string point, give the X, Y, and Z, and we will fill it out with the values from point.x, point.y, and point.z, and we will round each of those to 2 decimal places. We need to declare our member variables, so the client is no longer this type, so we will change that to my interfaces, service, trigger points. This shared pointer to a timer base is still okay. In the main entry point down here, instead of minimal client, this should be trigger points client. Let's save that. Let's go into package.xml. And as we did with the Python package, we need to explicitly say we are dependent on geometry messages so that ROS knows to include that ROS package. Let's Control S to save that. Let's go to CMakeLists.txt where we need to add this as a target. In fact, I'm just going to copy define ACC subscriber, and I'm going to change the names here. So instead of ACC subscriber, I'm going to call it trigger points client. That's the new target. Trigger points client is the target, and the source file is trigger points client.cpp. Let's make sure we link to the correct dependencies for the target trigger points client. So we need RCLCPP and my interfaces, and we will add trigger points client to the install list, and that destination should still be good. Let's save that. Let's go to View, Terminal, and we will build our CPP package. Looks like I've got an error here. What did I miss? So if we control click on this line, it should take us right there. I accidentally deleted one of these colons. So that should appear like a namespace within our class. Control S to save, up again on the terminal, run the previous command to build the package. Looks like it succeeded this time. So let's go back over here. Notice I am still running this trigger points service. In the other terminal, we need to source install setup.bash so that ROS2 knows about our new executable. And we will say ROS2 run my CPP package trigger points client. Periodically, that should send a request over to the server, which you can see it receiving here. It should be a random number of points being requested. So 3, 1, 2, 1, 10, 9, 10, so forth. The server should respond with those points. So every time you see success, it should list out the number of requested points under it, and the individual values, the X, Y, and Z in those points are also randomized. And if we let it run for a while, hopefully we get something with a 0. And interestingly enough, it looks like I ran into a bug here. I'm going to Control C to shut that down. Looks like I did not assign this correctly. So let's go to line 36 in my server. This is why we always run unit tests before deploying things. Here it is. Instead of request, this should be response. Let's save that. We will need to rebuild my Py package. Looks like that built. And let's rerun that. So the server should be running. Let's rerun the client. And let's wait a moment to see if it can handle received number of points being 0. And there it goes. We have the received num points being 0 here. And if we scroll up, sure enough, the server responded with success of false and then went right back to dealing with or printing out the points that it requested. If you want to challenge yourself, try making the nodes in the languages that we skipped. So for example, we made the accelerometer publisher in Python. Try making the similar subscriber. And if you go to C++, we made the subscriber, try making the publisher. For the services, we made the trigger points server, so try writing the client. And then in C++, where we made the client, try making the server. You will know it works because you will get a similar output to what we just saw in those terminals. ROS comes with a number of standard interfaces that I recommend using if you just need to pass simple types like single numbers, strings, and Boolean values. In many cases, however, you will need to define a custom interface for your particular use case, like bounding boxes for object detection nodes, or telling a group of servos to move to a set of positions. Because of that, knowing how to define custom interfaces is a crucial skill when working with ROS. In the next episode, we'll see how parameters can be used to change how nodes behave at runtime. See you then.